In this lesson, we add a region prefetcher that looks for 4 or more hits inside a 2 kibibyte region. Then we estimate its coverage on a tiled matrix multiply, and we compute the extra traffic that the prefetcher generates. Here are the rules we assume. A region is 2 kibibytes, which is 2048 bytes, equal to 32 cache lines of 64 bytes each. The prefetcher triggers after 4 unique cache line hits inside that region. For a single contiguous run that stays inside one region and uses L cache lines, coverage is max of 0 and L minus 4 divided by L. The wasted lines in that region are 0 if L is less than 4, 32 minus L if L is between 4 and 32, and 0 if L is at least 32. Let us build intuition with a picture. Suppose a contiguous stream uses 8 cache lines inside a single 2 kibibyte region. The first 4 are demand misses that arm the prefetcher. The next 4 are usefully prefetched. Because the region contains 32 lines, the remaining 24 lines are fetched but never used, and that is wasted traffic. Next, how does a tiled matrix multiply access memory? Consider tiles of size T by T, with row major layout and a good loop order. Each inner loop scans T elements contiguously along a row of A and T elements contiguously along a row of B. That means each inner run touches L equals ceiling of T divided by 8 cache lines, because each 64-byte line holds 8 double precision numbers. Let us start with T equals 64. Then L equals ceiling of 64 divided by 8, which is 8. Coverage per row segment is 8 minus 4 over 8, which is 1/2 or 50%. Wasted per row segment is 32 minus 8 equals 24 cache lines per row for demand lines, for useful prefetched lines, and 24 wasted lines. Per tile and per array, there are T rows each using L lines, so 64 times 8 equals 512 used lines. That expands into 64 times 4 equals 256 demand, 256 useful prefetched, and 64 times 24 equals 1,536 wasted lines. We do this for A and for B, so we double those counts when we look at both input arrays. Now try T equals 128, then L equals 16 cache lines per row segment. Coverage becomes 16 minus 4 over 16, which is 75%. Wasted per row is 32 minus 16 equals 16 lines. Per tile per array, there are 128 times 16 equals 2,048 used lines, 512 demand, 1,536 useful prefetched, and 2,048 wasted lines. The coverage improved, but the wasted traffic is still large. Finally, consider T equals 256. Then L equals 32, exactly one entire region. Coverage is 32 minus 4 over 32, which is 87.5%. There is 0 waste within that region because we use all 32 lines. This is the sweet spot for a region prefetcher of 2 kibibytes. Here is the coverage function as a function of L. It is 0 until 4 lines are touched, then it rises as L grows, and it approaches 87.5% when an entire region is consumed. Let us summarize memory traffic to dynamic random access memory for one tile multiply of A and B. Without prefetching, the traffic equals the unique lines actually used. With this region prefetcher, the traffic equals used lines plus wasted prefetched lines. For T equals 64 per array, there are 512 used lines plus 1,536 wasted lines. For A and B together, that is 2 times 512 equals 1,024 used lines, and 2 times 1,536 equals 3,072 wasted lines. The prefetcher multiplies the traffic by about 4x, which can overwhelm bandwidth. For T equals 128, the traffic roughly doubles. For T equals 256, the extra traffic is near 0. A statistical note. We simplified by assuming a row segment stays inside one region and starts near the region boundary. If the start alignment is random, some segments cross a boundary and may not trigger or may waste less. For long, truly contiguous streams, each 32-line region costs only 4 demand lines to arm, and the coverage approaches 87.5% with almost no waste, except possibly in the very last partial region. The qualitative takeaway is simple. Region prefetchers need runs that are at least one region long, to be efficient. On short runs, such as T equals 64 or T equals 128, they generate substantial extra traffic. Practical recommendation: if you deploy a 2 kibibyte region prefetcher with a 4-hit trigger, prefer tile sizes where T divided by 8 is at least 32, that is T around 256, for double precision. Otherwise, consider lowering the region size, raising the hit threshold, or using a stream prefetcher instead to reduce wasted bandwidth.